This lesson we're going to see what happens to light when it hits a curved mirror. We just investigated how a plane mirror works, but a curved mirror is a little more interesting perhaps, or at least different. I don't know about more interesting, but to begin with, we consider a light source that's a long ways away from the curved mirror. There's the curved mirror. This is a concave mirror. And the initial point I just want to make is that if the light source is sufficiently far away, then the rays that come toward the mirror, if you just look in this area here, just look at a little small slice of those rays, you can tell that they're very close to parallel. And the further away the object is, the closer that will be to becoming the truth. So, in which case, the rays converge at a particular point. Now this is true for the sun, moon, and stars. They're so far away that the light is so close to being parallel across the full range of the extent of the mirror itself that we can assume they're parallel. Now, so for a concave mirror, let's take a look. We're going to consider a circular segment of a mirror. And this is the principal axis here, going right through the center. Now, if we consider a circle centered here at C that passes through, it's part of the, where this circular segment is part of that bigger circle, we'll be able to see the geometry and how this works out. So, first of all, the distance portrayed here is simply the radius of the curvature. The radius of curvature. And now we're going to have a bunch of parallel rays. We're going to idealize and consider them completely parallel, coming and hitting the circular segment. Now, you're convinced, hopefully, that each reflection will obey the law of reflection. I hope you're convinced of that. And that a line drawn from any place on this circular mirror to the center is actually normal to the surface. I mean, it's a radius line, right? So from the center, you hit the edge that's exactly perpendicular to the surface itself. So it's normal. And so what's going to happen to the incident ray when it bounces? So there we have an incident ray, and this by opposite interior angles, we have it being the incident angle as well. And then we have the light bouncing. And this reflected angle is the same because it obeys the law of reflection. So this parallel ray coming in is not the same thing as light coming from the center, is it? Not at all. And so the bounce obeys the law of reflection, so it hits down here. And this has a very special name. It's called the focal point. And all of these rays will bounce to that location based on the principle of the law of reflection. Yay! Okay, so the distance from the mirror to the focal point is simply called the focal length. Focal point, focal length. Now, you see this triangle. These angles are the same. For those angles to be the same, it means it's an isosceles triangle. The sides are equal. It's the same angle for both. And there's the radius. Now, we run into geometric distortion rather rapidly with this analysis when we use a whole lot of the circle. And in general, in optical systems, you just use a small part of the circle, a real small part. So for small angles, we're not dealing with huge angles like we see here. It's just small angles, or in any case where the circle is real big and the curvature is small. All right. So if it's true, then that it's a small angle, then the focal length and the sides here is depicted are the same length. So that is the same length as this. You can imagine this circle coming out here and drawing a line from here way out here. It's like, well, it's not the same at all. But that's a huge angle we're talking about. So we're talking about regions real close here. Okay. So some preliminary conclusions that by geometry, the focal length is half the radius. Makes perfect good sense from our investigation of this here. These angles are the same. So it's halfway between here and here is where the focal point is. An object at infinity, the image then, is the place where the light focuses, where it all converges, and that's at the focal point. Now, the convergence of the rays from an object at infinity arrive at the focal point. However, many things in practical life are not at infinity, or even a very, very large distance away. So what if it's a lot closer, spatially extended? Will the image be at the focal point? Well, you could probably surmise that the answer is no. We'll figure it out, though, by drawing two rays that we know geometrically what's going to happen to those rays. A parallel ray, we just looked at that. A parallel ray must pass through the focal point, and a ray through the focal point, by similar logic, must then reflect back parallel. And when we consider the convergence of those two rays, the convergence tells us where the image will be. So let's do it. Let's do it. It's kind of a minimalist approach to figuring out what the image is going to be. So here's our circular mirror, and here is the center, and there is the focus. Here is the object. It's not nearly at infinity. In fact, it's between the center and the focus, so it's really close. It's just very close. Where is the image going to be produced? So we can define everything as we go along. So this is the height of the object. This is the actual object sitting there. In space and time, yes. So the distance to that object is, you guessed it, d of the object, the distance of the object, dO. All right. Now, here's our parallel ray. What does it do? We just learned it passes through the focal point. And I'm extending that because we're about to do another ray through the focal point. And by similar logic again, that will bounce parallel. Like if we shot a ray this way, it would go through the focal point. So the return trip is the same. Well, look at that convergence. We've just identified the image location for the tip of the arrow. And so really, we've identified the image itself. And you could prove it by doing the same thing we did with these anywhere along here. The middle point here would end up being right there. And a ray from this point, reflects straight back, go there. Okay, so anyway, it works. And then so we have the height of the image. And finally, we have the distance to the image. So there's the full geometry of the concave mirror. Isn't that awesome? Now, does light from the object actually pass through the location of the image? Yes, it does. Okay. And since we could answer yes to that, it means that the image produced is real. It's not virtual. It's also inverted. Obviously, it's upside down. Not virtual as with a plane mirror. Plane mirror produced a virtual image that was right side up, actually. Now here is another couple lines drawn that outline two similar triangles. All right, so we have the same angle here and here. We have a right triangle, so this is the same angle, so these are the same angles. All right. Now the ratio of those two heights, height object over height image, is also going to be the same ratio as the sides here, right? But the side ratios are object distance over image distance. Well, that's kind of cool. But we're not done. We're going to construct two more similar triangles here. Hopefully you'll agree those are similar triangles. We have all the same angles here as well. Okay. And by the way, here's where you can start seeing some of the distortion from too much curvature. So this is idealized. We would expect the curvature to be a lot less, so it really would extend clear out here. Anyway, some of the geometric dilution of precision going on there. Would you not agree then that since these are similar triangles, the height of the object compared to the height of the image, which is this ratio. Wouldn't that also be this side compared to this side? Of course it would. And so we have dO minus F over F. Well, dO minus F is the size of that side. dO minus F leaves us with this part. And then F itself is the other side. So there we go. That ratio holds true. Now I'm going to do a little trick. I'm going to multiply that last thing by 1 over dO. So if we multiply this by, this whole thing by 1 over dO, then the dO goes away on this side. You get 1 over di equals dO minus F over dOF. But look at this. dO over dOF is 1 over F, and minus F over dOF is minus 1 over dO. That there is a really useful relation. So the equation is as follows. 1 over F equals 1 over dO plus 1 over di. It's called the mirror equation. It relates the focal point, the object distance, and the image distance. It's kind of got everything there. That's a wonderful little equation. The magnification itself is really conceptually simple. It's just the ratio of the height of the image over the object. If they're the same, magnification is 1. If the image is bigger than the object height, then it's like you normally say it's magnified. But if it's the opposite of that, if the object is bigger than image, then it's reduced in size. Well, height image over height object is also distance image over distant object. And so that's also the magnification. And I'll bet you could guess what the negative sign means. That's right, it means it's inverted. So there you go. And now let's check to see what happens if you put the object inside the focal point. So we were outside of the focal point. We were here. We had a magnified image. And now we're going to go inside the focus. And let's see what happens. Well, let's throw a parallel ray. We know that goes through the focus. And now we need one coming from the focus, so to speak. In other words, we're going to consider a ray that is coming like virtually, so to speak, from the focus. Okay, so it's going to be going in this direction. So that's not the real ray. The real ray is right there, but it's as though it's going through the focus, which means it would bounce parallel. Now, do those rays converge? Survey said, no, they don't converge, they diverge. But what we're going to do is project backwards on both of them. They're projected backwards. Now where that convergence is, it's kind of like, again, a person looking here sees the ray coming from here. Likewise, if you put your eyeball over here, you see the ray coming from this direction. The convergence of those gives you the location of the image itself. The image is virtual because it's not real rays of light making that image or passing through that location. It's also larger, so it's magnified, so to speak. And now how about beyond the center of curvature C? So we did between C and F on the previous slide, and now we did inside F, and now we're going to go outside of C and put the object right here. Let's see what happens. Parallel ray shoots through the focus. Ray through the focus shoots parallel, and we've identified the image location. Oh, isn't it cute? Look at that cute little arrow. So it's real because the light actually passes through that location. It's inverted and smaller. All right, so there's the various possible situations. And we can conclude by commenting that if the object is inside the focal point, within the focal point, the image is virtual. It's upright and it's magnified. It's bigger than the object was. But that is an experience you've probably had because you stuck your face close to a makeup mirror, perhaps. Guys and girls, maybe. In any case, you see your image magnified. Yep, you do. If the object is beyond the focal point, so if the object is out here, or here for that matter too, the image is real. Actual rays of light pass through the point. It's inverted, it's upside down, and the magnification will depend on the object's position compared to, well, when it was between C and F, it was magnified. When it was outside of C, it was diminished. So it has to do with where the object is, depending on, with respect to the center, the radius, or the center of curvature. And so there is a brief but very, kind of inclusive overview of what happens with a concave mirror. And in our next lesson, we'll consider a convex mirror.